I actually wanted to talk about this for like a while now. Like I feel like there's how and like when will we ever reach to a state where programs will just fucking work instead of just having more issues? How can we create a system that doesn't fucking just fails all the time? I still don't know what is so wrong about Xorg. Like it feels like a fine standard to me. Maybe I'm just not getting it. A lot of people are saying it's bloated, but I feel like if you're building a whole fucking wrapper around it, maybe, just maybe, you have done something terribly wrong. Um, like, I think Wayland, like, I'm using Wayland right now. And the state of it is, it's not great. I don't know why can't we just add more things on top of Xorg. Maybe it's just people in the Xorg community are kind of burned out, but I don't know. It feels weird. The I don't know why like Wayland can just allow you to like capture a fucking window. Like it should be something that's incredibly simple, but for some bizarre reason we collectively has decided that no, we're not going to do that because of fucking security. Anyway, we're going back to the async Rust book. You might be wondering, oh, I thought you were going to read the Rust book first. Why are you going to why are you reading the async Rust book again? Because I feel like it's kind of hard for me to concentrate on like something that I kind of already know. So like I'm really at a very awkward spot when it comes to learning Rust, which is I've been using Rust for casually, not like a lot. I don't really do a lot of Rust programming, but I've been using Rust casually, most in synchronous context or asynchronous context with very simple logic, right? Not like crazy async that kind of requires you to like doing a lot. Like I was not doing UI stuff in Rust. It's such a pain in the ass to work with UI in Rust, but not UI stuff, but like async, fetch, and then you know that is relatively simple. If everything that's in your system can be described as pure function like a server, it's fairly simple. Even with async Rust, right? It's fairly simple. Just take something, output something, and you await it, and it's async. You don't have to concern about anything because it's runtime handles everything for you. But I'm trying to develop GUI application and I ran into a lot of issues. Anyway, I feel like if I want to continue on the current development, I probably should finish the async Rust book first, even if I will inevitably encounter a lot of concepts that I'm not entirely familiar with. Yeah, I mean, let's just read it. It's like a lot shorter than the actual Rust book. That one is like actually pretty huge. I'm not gonna read that. Task wake ups. Sorry. Every time I try to read, I just realize I can't read. Task wake ups and waker. Task wake ups and with waker. How can I misread so much in such a short? It's not even a sentence. It's just the title. It's common that futures aren't able to complete the first time they are polled. When this happens, the future needs to ensure that it polled again once it is ready to make more progress. This is done with the waker type. Each time a future is polled, it is polled as a part of a task. Tasks are the top level futures. Tasks are the top level futures that have been submitted to an executor. Waker provides a wake method that can be used to tell the executor that the associated task should be awoken. When wake is caught, the executor knows that the task associated with waker is ready to make progress, and its future should be polled again. Isn't that just like the other thing? Who's the other thing? Isn't that just isn't that just this function? Or am I just stupid? Maybe it's both. Who knows? Waker also implements clone so that it can be copied around and stored. Let's try implementing a simple timer future using Walker. Okay? Applied. Build a timer. For the sake of the example, we will spin up a new thread when the timer is created, sleep for the required time, and then signal the timer future when the time window has elapsed. First, start a new project with cargo new lib time future and add the import that we need to get started to this thing, which is future and ping. What is ping? I have no idea what is ping. Arc mutex, those are things that I've seen quite a lot, but I have no idea what they are. I mean, I know what they are, like arc is atomic reference counting and mutex is mutex, but I also know why you should use them, but like I also just don't. Task, context, poll, waker, thread, time duration, okay? Let's get started by defining the future type itself. Our future needs a way for the thread to communicate that the timer has elapsed and the future should complete. We use a shared arc mutex value to communicate between the thread and the future. Okay, we have a shared state, right? We have a time future shared state. The shared state that we have is a struct that has a bool with complete and the waker of waker. The waker for the task. The waker for the task that timer future is run on. The thread can be used. Can use this after setting complete equals true to tell timer future it's time to wake up. See that completed equals true and move forward. Okay, now let's actually write the future implementation. Future for time future. Type output is nothing. When polled, we have self ping. I have no idea what self ping is. It's a mutable reference to self. CX is a context. What is the context? Oh, it's task. Task context. Hacks. English sucks, man. I mean, to be honest, a lot of people are complaining about like, oh, English being so hard. But at the same time, it's also like one of the easier European languages out there, if you know what I mean. Anyway, implement future for time future. We have our self and our CX, and it's going to return a self.output, which is nothing, right? that shared state is this one. We're going to lock the shared state, and if it's complete, we're going to pull ready, and otherwise we're going to wait, what? Shared state dot waker equals sum cx dot waker dot clone. Okay, let's read the comment. This one is pretty straightforward. I guess this part is weird. It's kind of confusing. Set waker so that the thread can wake up the current task when the timer has completed, ensuring that the future is polled again and seeing that complete equals true. Set a waker. Oh, we need a waker. Yeah. It's tempting to do this once rather than repeatedly cloning the waker each time. However, the timer future can move between tasks on the executor. However, the timer future can move between tasks on the executor, which could cause a still waker pointing to the wrong task, preventing task future to wake up correctly. I mean, it makes sense, but it does feel like a very slow implementation though. I can kind of see why. I can definitely see why async and awaits are more associated with like single-threaded workload, because it is kind of expensive. You're trying to support multi-threading. MB. What is MB? I think I definitely know this. I'm just stupid. Usually not a banana. Using writing to indicate that something is important. Okay. I thought it was like notably, but apparently it's not. It's possible to check for this using the waker will wake function, but we omit that here to keep things simple. What? Possible to check. I have no idea what just happened. How does the will wake work then? Like, how does that work? Pretty simple, right? If the thread has set is completed as true, we're done. Otherwise, we clone the waker for the current task and pass it to shared state waker so that the thread can wake the task back up. Wait, why is the waker inside of the state though? Cause like why is the waker inside of the state? The thread can use this waker. I don't see this waker thing being used anywhere else in this code. It does not make any sense to me right now. Maybe I just need to read more. Okay, we're done. Otherwise, we clone the waker and pass it to the waker so we can wake it up. Importantly, we have to update the waker every time the future is polled, because the future may have moved to a different task with a different waker. This will happen when the futures are passed around between tasks. What? This will happen when the futures are being passed around between tasks after being polled. I guess I'm just still kind of confusing. I mean, conceptually I understand it, but like I don't understand it. I'm retarded. Finally, we need the API to actually construct the timer and start the thread. Implement time future. We have a new duration. We're gonna create a new state. Deep state. Share the state. Share the state. That is like anti-state, right? What is the opposite of deep state? It's like shallow state. Oh my god, shallow state. Weak state. Oh my god. Oh my god. Shallow state mention. Alright. Spawn a new thread. We have a share state. We're gonna clone it. We're gonna spawn a new thread. We're gonna move it here. Thread sleep duration, and then we have the shared mutex. We're gonna lock it if it's completed. What? Let some waker. Ah, we're calling the waker here. Wait, I still don't get it. Oh, I think I get it now. Because it's running on a different thread. And we have the state. And if it's completed. Wait, what? Oh, we're going to set it's completed to true here. We are not reading it. I for some reason thought we were reading the it's completed state. That makes a lot of sense, actually. That makes a lot of sense. What? That's all we need to do to build a simple timer future. Now, if only we had an executor to run this future on. Okay, that's exciting. Exciting, I would say that's pretty exciting. How do you... I think this is just called what, right? What? Meaning.
Woot.
Woot. Okay, woot. Let's go. Applied. Build an executor. Rust's futures are lazy. They won't do anything unless actively actively driven to completion. One way to drive a future to complete is to awake inside of an async function. But that just pushes the problem one level up. Who will run the future return of the top level async function? The answer is that we need a future executor. Future executors take a set of top level futures and run them to completion by calling pull whenever the future make progress. Typically, an executor will pull a future once to start off. When futures indicate that they are ready to make progress by calling wake, they are placed back onto a queue, and pull is called once again, repeating until future is completed. Until the future has completed. That is hard to read. I can't read. Oh, jeez. In this section, we will write our own example, our own simple executor capable of running a large number of top-level futures to completion concurrently. Wow, that is so fascinating. For example, we depend on the futures crate for the arc awake trait. What is the futures crate? Let me try to... What is that? Futures. Here we go. This is what it is. Wow, that's a fancy name right there. Futures RIS is a library providing asynchronous. One works without standard library. That's fancy. Okay. Next, we need to have the following imports at the top of source main.rs. A future, we have box future, what is this? We have Waker reference and arc wake. Is arc wake just this? Like, what is arc wake? It's just like, is it just like arc and the mutex and then wait, I don't know. I don't know. I don't know. We also need this the standard library. We got the future from future, got sync. What is MPSC? Sync channel receiver sync sender. What the fuck is that? Sync, we have arc and mutex again. We also get tasks. We have task context and time duration. We have gonna use the timer for some reason. Our executor will work by sending tasks to run over a channel. Okay, over a channel. What is a channel? The executor will pull events of the channel and run them. This is a kind of interesting expression. When I was in like high school, I learned an expression of like based off of. It's not a standard. It's not in the standard English. It's not in the, or it's not in the textbook that we were being told. But you know, language learning is a funny process. Anyway, let's get back to the topic, which is, well, I guess I'm still trying to learn the language right now. It's just Rust. It's not a human language, it's a programming language. That is not funny. The executor will pull events off of the channel and run them when a task is ready to do more work. Is awoken. It can schedule itself to be pulled again by pulling itself back onto the channel. In this design, the executor itself just needs the receiving end of the task channel. One thing I'm kind of curious is like, since the timer implementation we have uses a different thread, I'm kind of interested in like the performance of this. I mean, I can only imagine this performance gonna suck ass, but if we're not spawning things on the new thread, what should we do? Like, I have no idea how to do that. Which is peculiar. In this design, the executor itself just needs the receiving end of the task channel. The user will get a sending end so that they can spawn new futures. The tasks themselves are just futures that can reschedule themselves. So we will store them as future paired with what? So we will store them as a future paired with a sender that the task can use to requeue itself. guess I'm kind of confused. Store them as a future paired with a sender that the test can use to requeue itself. What does that mean? What does that mean? I actually had I was thinking earlier today about like building my own programming language in Rust, because like Rust has a compile command, not compile, like build script. So I'm kind of thinking about like using that. I can write my own programming language and use tree seeder or whatever and translate that to Rust, and then having Rust to compile my source code, which is compiled to Rust, and then it got a compiled language that is memory safe. Very interesting. And I was thinking about language design a lot recently. I thought I was thinking about like, what do we want for what do we really want for some what do we want for distributed systems? So I was thinking about like every function being a queue. So like it's a public queue which you can call other process, and all the arguments and return values will be passed through the some kinds of RPC call. Right, every function will just be like an RPC call. It's definitely going to be like fucking slow, because like everything is done through the network. But at the same time, it can also scale pretty much infinitely, right? Because like, forget about like multi-threading, forget about even like running on the same machine if all we have are a bunch of like pure functions. And because like a lot of websites these days are pretty much just running on like database, right? That's all they do. Like all they ever do is to write a fucking API to connect to a database somewhere. I was kind of thinking, and for the most of the part, the API interface that is exposed to the end user is pure, or at least most of them are acting pure, right? Because that's how how do I say it? That's how languages like Haskell are getting such a popularity in like large systems, right? So, but it's kind of thinking about that, having all functions being pure and all functions running off of RPC, and it can also like when the program starts, you can kind of initialize a list of like other hosts, and we just like, I mean, you can do like more complicated behaviors, but like you can just like randomly distribute tasks among them, and hopefully you'll have a system that is like insanely scalable. Or the only thing that's kind of bottlenecking the whole thing is your router and your switch, which is common. But I guess that's not the most performance way, but but again, that's not the most performance way, and kind of begs the question of, okay, why do we want microservices, these nuts everywhere? That's a good question. And I was thinking like, maybe if every function is pure, just maybe we can kind of like do like lambda reductions on them and turning them into like, if it's able to run on the same task, if it will like do automatic inlines for everything that's possible. If it's not possible to like automatically inline it, or just try to assign it to like a different server. I think that's a fun idea. I'm pretty sure someone has done it before. Actually, is there a language designed for distributed systems? Okay, it's a actor-based language. Oh, it's a fucking paper. What the fuck? What is it? It was released in 2012. Wow, that's a long time ago. That's like a decade ago. Let's see what they have to offer. They wanted high performance and low stateful serverless programming. I don't know. I was thinking about like all the states that the program has. Like I mean, imagine like once I compile this, it's gonna run on like all different machines, or like even if it's running on the same machine, you can like spawn 10 different processes and processes. How do you say that? You can spawn like 10 different processes, and it's going to run on different cores, and you like kind of communicate with them through network interface, just like you would with like a different physical computer. And if you want to mutate anything, you can use something like Redis, right? You can use something like Redis, and yeah, every mutable thing has to be done through some other service. The programming language itself only concerns with immutable stuff, which is like your business logic, which I think can be fun. But that's like a huge undertaking, or maybe not. But it feels fun to think about. Where the fuck are we? Our executor will work by sending tasks over channel and executor will poll. Okay, I read that before. In this design, the executor itself just needs the receiving end of the task channel. The user will get a sending end so they can spawn new futures. Okay, I think I also read that myself. Task executor that receives tasks off of a channel and run them. Okay, we have a queue, the receiver, and the arc task. I thought we have that's arc awake. That's arc wake, right? I don't know. A future that can reschedule itself to be polled by an executor. Future. Box future. Sync center. What is a sync center? I think I might still have to read the Rust book, but I just really don't want to read the Rust book. I just really don't want that. I have a new executor and spawner. I have a executor and spawner. Have this many execute tasks. We have sync channel. Gonna create that many channels. Wait, so Rust does have channels. Is it the same as the Go channel? I don't know. Let's also add a method to spawner to make it easier to spawn new futures. This method will take a future, box it, and create a new arc task with it inside which can be enqueued onto the executor. Actually, the fucking queuing distributed language, I'm actually having like a lot of ideas about it. Like, you can have like a use the what is it, gRPC, use gRPC, and every like protocol can like be automatically generated. It just has like a version string that is like a hash of like the program. So like it kind of ensures all the functions are running on the correct version. If it's not the correct version, it's just gonna break. I don't know. And like I can also because it's written in Rust, like the code that's been generated is in Rust. Theoretically, you can just have like a library in Rust that I can use to like call that distributed system the same way that that language itself work. It's a very fun concept. It's a very, very fun concept. I'm not sure how feasible it is though. I don't know. I think I have to stop mentally ejaculating all of this shit. But at the same time, I feel like I really don't think. Here's a hot take. I think all the microservices are fundamentally evil. Because like they're not faster, right? I feel like microservices are scams, right? They're not faster. They requires more resources. You spend more time waiting just for the fucking server to respond. And serverless is the biggest scam. Like you're gonna try code start a new, like especially when you're writing fucking JavaScript, you're gonna start a whole interpreter, run a single function, return it, and nuke the fucking container. Like, how is that possibly a good idea? Who the fuck thinks this is a good idea? It's hard to debug, it's hard to maintain, it's slow, it's expensive, and it's maybe the advantage is that it's scalable. You can make an argument saying it's scalable, but I guess it's just scalable. But like for the good majority of the services, right? For the most services out there, you do not need this fucking scalability. You just fucking don't. You don't have users all around the globe. Here's the thing. If your startup doesn't even have like localization for like 20 different languages, you probably don't need that. Because your user bases are probably just concentrated in that few countries, right? Your customers are mostly probably just gonna be in the States, right? Or sometimes Canada, right? Right? Am I crazy for thinking that way? Am I the crazy one? Do we really want instant fucking response, global wise? And to achieve that, we have to use fucking Cassandra, like distributed database, distributed fucking Lambda expression, distributed serverless microservices. Like, I don't know. Maybe I'm just too stupid to understand any of this. I don't fucking know. Anyway, let's also add a method to spawner to make it easy to spawn new features. This method will take a feature type, box it, and create a new arc task with an inside which can be queued onto the executor. Wow. I actually just don't get it. What is boxed? Or turn into a box? What is future? Future implements future. Output equals null. Static. Send. There's a lot of lifetime going on, and I don't know Rust enough to know about its lifetime. I really should read the Rust book. I really should, but I really don't want to. Self-task sender, send task, expect too many tasks are queued. Okay. To pull futures, we will need to create a waker as discussed in the task wake up section Wakers are responsible for rescheduling a task. Wakers are responsible for rescheduling a task to be polled again once wake is called. Remember that the wakers tell the executor exactly which task has become ready, allowing them to poll just the futures that are ready to make progress. The easiest way to create a new waker is by implementing the arc_wake trait, and then using the wake ref or into waker functions to turn an arc_impl arc_wake into a waker. What is the arc_awake trait? Where is it? Where is it used? Okay, it's down there. Let's implement arc_awake. I think the problem with like using packages in a tutorial is that I don't understand how that is implemented, and just based off of what I've seen, it does seem like it should be easy. Like it's obviously so easy that the writer of this book is not even like willing to the writer of this book is not even willing to include the part where they come up with the idea of like writing this, because it's so obvious. But for someone with 0 IQ, I don't understand it. Like by ref, we have arc_self, implement wake by sending this task back to the task channel. It's gonna clone itself with the arc. It's gonna task sender. What is task sender? I only know Bernie Sanders. What is task sender? Oh, it's it's the same task sender from the spawner. Okay, got it. Makes a lot of sense. Send clone. Expect too many. Oh, okay, that makes sense. It's just like a queue. So it's just if I'm understanding correctly, this is just like round robin, right? Or maybe not. Is it? Is it? Is it like that, or is it like round robin? I'm kind of wondering what happened if the queue is empty and no task is like ready to make any progress. So it just stops there? I don't know. Like, do you just wait it? I guess we will have to. Okay, we are in the loop here. Nice. When a waker is received from arc task, calling wake on it will cause a copy of the arc to be sent onto the task channel. Our executor, when needed, our executor then needs to pick up the task and pull it. Let's implement that. So, self-ready queue. What is ready queue? Bro, I'm gonna get ridiculous. Oh, so it's really just like the I really don't understand the syntax here. What is sync channel? I think it's from the sync package, right? That's from this thing. I don't know what this is. I would just imagine it's something similar to a Go channel. I'm just assuming that. Can be totally wrong. What else? I feel like modern software has a lot of complexity complexity in it. And a lot of people are saying, oh, but it's just unnecessary complexity, but maybe not. Like, how else would you implement something like this? It doesn't seem like something that's very plausible, to be honest. And another question that I kind of have is like, so Rust still has the channel thing that Go has, right? Is that am I crazy, or like can you just implement something like this in Go and like expect it to like, or maybe not, because like you can't really async is like a syntax feature rather than a actual one. But I don't know. When Waker's our executor then needs to pick up the task and pull it. Let's implement that. Congratulations! Another thing that's really annoying to me is how Rust doesn't have an official async executor. At some level, I can see why they don't want that, because like you want more flexibility for your asynchronous thing. But like on the other hand, if everything is fucking incompatible with each other and everyone's just using Tokyo, maybe we should have an official runtime instead of just having. And also like the what's that, the async std is just, it's not even std, it's not even the same library. Like, I don't know. Anyway, congratulations, we now have a full we have a working future executor. We can even use it to run sync. What did I get? Just got a new email. What did I get? Oh my god, it's Steam. Got a special promotion here. What is it? Log into it. There are like some random people trying to add me on my Steam for some reason. I don't really get why people would want to do that necessarily, but apparently people are doing that, which is kind of wild. Special discount. What is having a special discount? It's not even showing, it just shows a price. Can I... Oh yeah, it's Beholder. Okay, Beholder is on sale right now, which makes sense. I probably should play Beholder sometimes in the future, but should I buy it now? I don't think I should buy it now, even though it's dirt cheap. The offer ends on... I mean, we can just wait and see what will happen. Anyway, let's be back to the... Congratulations! Now we have it. Okay, we're ready. We can even use it to run async await code and custom features, such as the timer feature we wrote earlier. Wait, are we having two different features? I thought we have the same feature. Oh, never mind that. Oh, okay, yeah, all the async function just returns a future. Interesting. Drop spawner. Excuse me. No. Why do we need to drop the spawner? Wait, why are we... Hold on, why are we dropping the spawner before... Before it's run? We ran it. Wait, how does the spawner work? How does the spawner work? The spawner is created from new executor and spawner. And the way that it works is you have a test scanner. I don't get it. Why are we dropping the spawner? What's the point? Is it not going to return if... I don't know. I'm kind of confused, but I don't know. I really should read the Rust book. I know I've been saying that forever, but I really do think that is something that I kind of have to do. And I just really don't want that. Executors and system I/O. In the previous section on the future trait, we discussed this example of a future that performed an asynchronous read on a socket. Have a socket read. Struct. Oh, whoa, what happened? In previous section of the future trait, we discussed this example of a future that performed an asynchronous read on the socket. Yeah, we definitely have that. This future will read the available data on the socket, and if no data is available, it will yield to the executor, requesting that it task to be awoken when the socket becomes readable again. However, it's not clear from this example how the socket type is implemented, and in particular, it isn't obvious how the setReadable callback function works. How can we arrange the wake to be called once the socket becomes readable? One option would be to have a thread that continually checks whether socket is readable, calling wake when appropriate. However, this would be quite inefficient, requiring a separate thread for each blocked I/O future. This would greatly reduce the efficiency of our async code. That's true. In practice, this problem is solved through integration with an I/O-aware system blocking primitive, such as epoll on Linux, kquick on KQ on FreeBSD system and macOS, IOCP on Windows, and ports on Fuchsia. Oh, Rust even support fucking Fuchsia. God damn. Yeah, I'm kind of curious about Fuchsia. What's going on with Fuchsia? Why is no one using it? I thought Fuchsia is going to be the future of our operating system. What happened to it? What happened to Fuchsia, actually? I need to know. I feel like, what happened to Fuchsia? It's in production right now, right? Like the Futra. Is it Futra? I think it's in production right now. Why the fuck is the Future logo looks just like Fedora? It looks pretty much the same as Fedora. Let's see what we have for Future. At Dart Runner, we have Elf Runner. What is Elf? I see like Elf fucking everywhere. Why is that everywhere? System core, we have kernel, Zirking, boot fs, user boot, fs host, we have package fs, product driver. I don't know. Yeah, what happened to Fuchsia? It's in the Google Home devices right now, right? But I just cannot imagine it offers like a significant performance benefit over something more traditional like Linux. Because Linux is not, I mean, Linux is kind of bloated for like low power devices, but like the hardware that's running Fuchsia, it's not low power though. Like they specifically have like shitloads of like web darts and other shit running on top of it. Like that's a lot of bloat. I'm pretty sure Linux can be more lean than that if you're not using GNU. Yeah, where are we? Yeah, we have the platform-specific features, and all of which are exposed through cross-platform Crust. Mio! Mio-chan. Do you get a Nichijou reference? Nichijou reference? Are getting a Nichijou reference? I'm so excited. Mio! It's a fast, low-level... Mio. Fucking Mio. That is so funny. Mio Nichijou, and this is how you know. This is such a weeb moment. To be fair, I feel like for someone to name their runtime Tokyo, have to be kind of a weeb. But I don't know. These primitives all allow a thread to block on multiple asynchronous I/O events, returning once one of the events completes. In practice, this API usually looks something like this. The struct IO blocker with events, which is signals. This one's so random, but I was thinking about a meme of like when your doctor call you an introvert instead of a sigma male. Oh my god, it's so bad. It is so bad. I can't I can't do it. Implement IO blocker. We get a new IO blocker. We have IO event interest. We have the object of this event. I don't get it. How is that supposed to make any sense? Make that make sense. Block. Okay, yeah, I mean, yeah, that makes sense actually. Uh, I was reading too fast. Futures executors can use these primitives to provide an asynchronous I/O object, such as sockets that can configure callbacks to be run when a particular I/O event occurs. In the case of our socket read example above, the socket set readable callback function might look like the following pseudocode. Your pseudocode looks like Rust. Your pseudocode looks like Rust. We can now just have just one executor threads which can receive and dispatch any I/O event to the appropriate waker, which will wake up the corresponding task, allowing the executor to drive more tasks to completion before returning to check for more I/O events. One thing I'm kind of interested in is like, no, never mind. The top level one is using the channel thing, right? I would just assume that one. Is channel a built-in OS feature, or am I just imagine that? I think that might be a built-in OS feature. Like one very unexpected OS feature for me is the signal. The signal feature is so confusing to me. Like, and I also feel like it's just not reliable, because like C is just not a reliable language, and you have such a fancy feature for such an unreliable language, it's ended up with something really, really unreliable, like what is that vulnerability that has something to do with signal in SSH? It's not the XZ one, it's like a different one. It's just the way that the way that SSH, Open SSH was implemented kind of results in a very silly, the SSH retry thing. Anyway, async awaits are special pieces of Rust syntax that make async awaits are special pieces of Rust syntax that make it possible to yield control of the current thread rather than blocking, allowing other code to make progress while waiting on an operation to complete. These are two main ways to use async fn and async blocks. Each returns a value that implements the future trait. Alright, we have this and this. Oh, this is just a block. I thought it was like a function, but it's not. As we saw in the first chapter, async bodies and other features are lazy. Yeah, they're lazy. They do nothing until they're run. The most common way to run a feature is to await it. Then a wait is called on a feature. It will attempt to run it to completion. If the feature is blocked, it will yield control to the current thread. When more progress can be made, the feature will be picked up by the executor and will resume running, allowing the await to resolve. Async lifetime. I think this one is the most interesting one by far. But I guess I'm kind of think I won't be able to get this one. But I will give my best shot. Unlike traditional functions, Async functions which make references or other non-static arguments returns a future which is bounded by the lifetime of the argument. Async functions which make references returns a future which is bounded by the lifetime of the argument. I mean, yeah, duh. They're gonna return the fucking future. This means that the future returned from an async function must be awaited, while its non-static arguments are still valid. In the common case of awaiting the future immediately after calling the function, this is not an issue. However, if storing the future or sending it over to another task or thread, this may be an issue. Yeah, this is the exact issue they ran into. I hate multi-threading. We should just all go back to the good old days of single thread and like have a 10 gigahertz CPU. Yeah, where's the 10 gigahertz CPU? We need that. Those Intel people are using P cores and E cores. Those are just a bunch of goobla, right? What we need is not those like nonsense. What we actually need is 10 gigahertz of a single core, right? Just imagine the potential there, right? Just imagine it. We can have a superheated die. Just imagine it. And then we can have like a fucking liquid cooler over there, and just to have 10 gigahertz 10 gigahertz CPU. Like it's just so sad that our CPU has kind of stuck at the same clock speed for the past few years. They're not making progress. Said by a CS people, said by a CS person. And some of the ECE people are gonna say, go fuck yourself. We're making tremendous progress, unlike your software people. And like you software people, you're soft, and we are hard. It's not even funny. Where are we? One common workaround for returning an async function with reference as argument into a static future is to build the argument with the cell to the async function inside of the async block. What? What does that mean? One common workaround to turn an async function with references as argument into a static future is to bundle the argument with the call to the async function inside an async block. Am I crazy, or this just doesn't make any sense? Oh yeah, this actually makes sense. Never mind. By moving the argument into the async block, we extended its lifetime. I don't even know why I'm laughing, but I'm laughing. I think this is hilarious. We extended its lifetime to match that of the future return from the cell to good. What is good? What is good in lifetime? I have no idea what is good in lifetime. Maybe I'm just too stupid to understand Rust. Just too stupid to be a Rustacean. Async move. Async blocks and closures allowed the move keyword, much like common closures. An async move block will take ownership of the variable it references. allowing it to outlive the current scope, but give up the ability to share those variables to other code. Wait, they're not taking ownership of it, are they? Where's the async move? Oh, they moved the string. Awaiting on a multi-threaded executor. Note that when using a multi-threaded future executor, a future may move between threads. So any variables used in async bodies must be able to travel between threads, as any await can potentially result in a switch to a new thread. This means that it is not safe to use RC or RC cell or any other types that doesn't implement the SAN trait, which including references to types that don't implement the sync trait. It just dropped a bunch of words that I have no idea what it is. Does it mean that we have to use the arc? I think that's what it means. Great. It is possible to use these types as long as they aren't in scope. As long as they aren't in scope during call to await. I don't know what it's talking about. I don't know what it's talking about. Similarly, it isn't a good idea to hold traditional non-future await lock across an await, as it can cause thread pull to lock up. What? Similarly, it isn't a good idea to hold traditional non-future await lock. So that's why you always need the fucking arc mutex. How, if you always need arc mutex, how about you just make it a single thing? How about that? Have you ever thought about that? Allowing another task to attempt to take the lock and cause a deadlock. To avoid this, using the mutex in future lock rather than the... Oh! Okay. So the arc mutex lock is not the... It's not the same mutex. Is that what's causing my issue? This is wacky. This shit is wacky. We're on chapter 4. We're a third of the way there. No, we're not a third of the way there, but I like to think that way. Want to stay positive. I guess that's all for today's video. It's been like, what, an hour? That's a long time. I don't know. I think that's pretty much all for today's video. It's kind of weird that they say today's video because I record multiple videos a day. But yeah, that's pretty much all for this video. Yep, that's about it. That's about it. See ya.